There is an ever-growing need to act against climate change, with global average temperatures rising year on year. Innovative solutions to reduce greenhouse gas emissions are vital. Globally, energy use accounts for around 3/4 of greenhouse gas emissions, with energy use within buildings making up around 1/4 of this. This project aims to optimize energy dispatch of buildings modeled as a multi-energy system, MES, and to validate the approach. Optimizing using MES models provides benefit not available in other methods, as the interaction of different energy sources, conversion between energy types, and variable energy costs are considered. This allows clients to better utilize existing infrastructure, as buildings are inherently multi-energy systems with benefits like reduced running costs and more effective dispatch of distributed generation.
To meet this aim, 7 high-level objectives were created, consisting of reviewing literature, modeling MES, optimization of various criteria, predicting future demands, implementing an MES controller, and implementing an MES emulator. Finally, evaluating performance qualified the work conducted.
The block diagram shows the developed system split into its constituent parts. The MES emulator shown in yellow and the MES controller shown in purple and grey. Model predictive control was used as it allows continuous optimization over a set period or horizon that moves forward in time. Each iteration, the controller, after implementing the first step, re-optimizes over the new horizon, accounting for new sample data, resulting in better decisions. To maximize the impact the controller decisions have, building consumption forecasts are required. A neural network was developed and trained using historical datasets that provided robust and accurate predictions of demand.
The emulator shown in yellow has been developed in place of a real MES, as controlling real physical systems can pose significant risks to potential clients. This is especially important while testing of the controller is still ongoing. Therefore, the emulator is also the team's testing environment, which both validates the controller's actions and generates the starting conditions for subsequent optimization. For this, a library of dynamic thermal and electrical component models were created that offer a more realistic response. After implementing the design framework, both the controller and emulator were configured to work in partnership.
A dashboard has been developed to display live and updating operating metrics to end users, providing a comprehensive overview of controller performance. For example, virtual meters showing consumption, controller future decision plots, and forecast error over the last 24 hours. The controller and emulator responses were validated using 4 case studies, and a summary of the findings are described here and shown through the user interface.
The complexity of the MES was steadily increased, with studies carried out both in winter and summer to ensure system reliability throughout the year. Initial studies were conducted on this MES. The results obtained validated the controller's operation as fixed demand was met and room temperature was within the predefined range throughout the week simulated. The emulator gave the overall actual component use and room temperature, which again validated both the controller and emulator's operation. As seen here, the boiler was consistently favoured over the heat pump by the controller due to the cheap gas import costs compared to electricity.
When local renewable generation in the form of solar was integrated into the multi-energy system, along with flexible electrical demand that was both schedulable and interruptible. To observe the effect solar generation had on the optimal dispatch clearly, a large array of 1 megawatt was used. In the scenarios constructed, solar power was used to help meet fixed electrical demand, which reduced multi-energy system running costs for the week by around £700 in the summer and £150 in the winter.
When SI demand was integrated, it was met by the MES when electricity import price was lowest over the scheduling period. The team concluded that significant savings could be made when allowing demand to be met in this manner, saving around £100 over the course of a week. Finally, the robustness of the framework was scrutinized by implementing this complex MES. The resulting response from the emulator's perspective revealed that all 7 room temperatures were kept at the upper boundary, as the inclusion of CHP enabled for surplus electricity to be dispatched cheaper than importing electricity from the grid.
Overall, the project has achieved what was set out in the initial scope and beyond, with a considerable amount of development work on both the scalable and adaptable MES controller and emulator being completed. The core objectives and much of the stretch goals have been met, such as the development of adaptable demand predictor, renewable integration into the framework, and flexible demand control. On the other hand, optimization based on multiple criteria was not achieved